We're going to go over a concept called enthalpy. So our learning goal today is just to kind of understand how enthalpy will affect the reaction type. Okay, so we're going to involve a term called enthalpy and how it relates to chemical reactions. So first off, we'll discuss calorimetry. So calorimetry is just the measurement of heat flow in and out of the system during a chemical or physical process. What this means is calorimetry is just measuring how much heat is either going in or out of the system when a chemical or physical reaction is happening. Now, because we know the system and the surroundings are basically all together in the universe, so when heat is released by the system, it goes out to the surrounding, which means if it's released by the system, it's absorbed by the surrounding. The opposite would be true too. If it's absorbed by the system, that means it's been released by the surrounding. Okay, so again, you could think of if you have like a cup of water, okay, and the water is hot, it starts to radiate out heat in all directions. So as it radiates out heat, the heat from the water or the system is being released. But then that means the surroundings are absorbing that heat. So when we talk about heat, we're really talking about something called enthalpy. So when the pressure remains constant, the heat we are going to call the enthalpy. Okay, and we're going to denote that with delta H. Again, this means change. So we're going to be talking about the change in heat since we know that calorimetry is a measurement of that change. So enthalpy is going to talk about heat either being released or absorbed by the system. So we've talked about how Q represents, heat in general. Since heat and enthalpy are essentially the same thing, we can say that our Q of our system is equal to delta H. Well, as we learned in the previous section, the Q of the surrounding is equal to mass times specific heat times the change in temperature. Since the heat of the surrounding and the heat of the system are going to be opposite because one's going to gain that while the other one loses it, you can say that the Q of the surrounding is equal to negative Q of the system. Okay, so they're opposites. Since delta H is the Q of the system, and this is equal to the opposite of the Q of the surrounding, you can actually solve for delta H, or the enthalpy, is equal to negative mc delta T. Okay, so now we have an equation in order to solve for the delta H of a reaction, or the enthalpy. Very similar to the heat that we've already gone over, but this time we can attribute that to the enthalpy. So let's do a practice example here. When 25 milliliters of water containing 0.025 moles of hydrochloric acid at 25 degrees centigrade is added to 25 milliliters of water containing 0.25 moles of sodium hydroxide at 25 degrees centigrade, a reaction is going to happen. So we want to calculate the enthalpy change in kilojoules of the reaction if the highest temperature observed is 32 degrees centigrade. And we're going to assume the density of the solutions is 1 gram per milliliter. So there's a ton of information here. As always with any problem, we want to break down what we're given. So if we take a look here, okay, we have to solve for the enthalpy change. Okay, so that means we are looking for delta H. As we just learned, delta H is equal to negative mass times specific heat times the change in temperature. So if we're going to look for the enthalpy, we must find the mass, specific heat, and change in temperature. Well, considering these solutions are happening in water, you can say that the C of water here, a value that you could just go ahead and look up, because specific heats are specific to each substance, well, this is equal to 4.184 joule per gram centigrade. Okay, so the C you just look up. This is something that you just find in a table. Okay, so what other information are we given here? Well, we're given that the initial temperature, so we're going to put initial, sorry about that, initial is equal to 25 degrees. We know the final temperature is 32 degrees. We know the volume of the water in HCl is equal to 25 milliliters. And we know the volume of water with the hydrochloric acid is also 25 milliliters. Okay, so we've got our C. Since delta T is equal to delta T final minus initial, our change in temperature is 32 minus 25, so 7 degrees centigrade. Now all that's left to find is the mass. All we know so far is the volume. So we know that the volumes are 25 and 25, so combined the total volume is equal to 50 milliliters. We know the density is 1 gram per milliliter. So the M is going to equal to 50 milliliters times 1 gram per milliliter, which is 50 grams. Great. So now we can calculate our enthalpy because we have our mass, our change in temperature, and specific heat. So delta H equals to negative 50 times 4.184 times 7, which in the end equals to negative 1.5 kilojoules. And there you have it. Okay, so you can actually calculate the enthalpy or the heat change in the reaction. So when we do talk about reactions, we're going to now discuss thermochemical equations. These are chemical equations in which we actually include the enthalpy. Okay, so you can include the enthalpy as either a reactant or a product here. We're going to refer to this enthalpy as the heat of reaction, delta H with a subnote Rxn for reaction. This is the change in heat of a reaction. So it can either be a product or a reactant. Either you're adding it like you would a reactant, or you're making it like you would a product. So if you take a look here in a thermochemical equation, you can see that this enthalpy, the heat, is on the product side because it's being released, it's being made. You can also represent it another way, just given the regular reaction, and then on the side indicating what the delta H is. Okay, we'll see why it's negative here, but a plus sign up there in a moment. Okay, these are just two ways that you can write a reaction. So when we talk about the heat of reactions, or the enthalpy of reactions, we're looking for delta H. So delta H of the reaction is given by the heat of the products minus the heat of the reactants. Okay, that delta sign always means final minus initial. So when the heat of the product is greater than the heat of the reactant, okay, so you get a big number minus a little number, you get a positive delta H here. Well, if the products now have a higher heat than the reactants, it means heat was added to the reaction, which means heat was absorbed, or a reactant. Okay, so we're going to put heat added to reactant side, because it had to be absorbed. And we know that processes in which heat is absorbed are endothermic. On the other side, should the heat of the products be less than the heat of the reactants, okay, you get a negative delta H, since it's now small number minus big number, and that means that heat is being released. Okay, so heat is on the product side. And because heat is being released here, a negative delta H would symbolize an exothermic reaction. So if we go back to the previous slide here, you can see that the delta H is on the product side. This means the heat has been released, which means it's exothermic, which relates to a negative delta H. Okay, so even though you see a plus 65.2 kilojoules here, the fact that it's on the product side means that it's a negative delta H because it's released. So when we talk about thermochemical equations, okay, we're going to include two things. One is the fact that the stoichiometric coefficient always refers to the moles of a substance. Okay, what that means is that the coefficients that we see represents how many moles of each thing there are. The enthalpy of the reaction indicates how much heat is either absorbed or released in the reaction per mole. Okay, and then if you flip the reaction, you flip the sign of delta H. So here we're actually going to be able to quantify the delta H of the reactions, okay, based on how many moles are involved or not. One last thing I want to touch on before moving on here. If we were to indicate, okay, the delta H over time, okay, and we have our reactants, okay, and the delta H is increasing over time. You can see here reactant, here's your product. Because there was a gain in the delta H, the product is now larger than the reactant. We would indicate that this has a positive delta H to it, because the products have a higher enthalpy than the reactants. So this would be what's called an endothermic curve. On the opposite side, okay, delta H over time, should the reactants have a higher delta H than the product, okay, this would indicate a negative delta H and an exothermic reaction, because now you can see that heat has been released. Okay, so when we talk about the delta H in reaction, we're going to look for a lot of these things here. So we can represent this change by a curve, by a quantity. Okay, so we're going to just kind of focus on how the products and reactants kind of relate to the sign of the delta H. Okay, so let's do an example here where we're calculating the delta H in a thermochemical equation. So we want to know how much heat is released when 300 grams of oxygen combines with excess white phosphorus P4. So we're given this reaction here, and we know here that 313 kilojoules is being produced or released in this reaction. So this is going to be our delta H. Okay, you can also write it as, because it's a product, negative 313 kilojoules, and this is going to be per mole. Okay, so if we have 300 grams of oxygen, we need to figure out how many moles this is. So times 1 mole over 32 grams, the molar mass of oxygen. Well, that's 9.375 moles of oxygen. Okay, so now we know how many moles of oxygen we have. We need to figure out how much heat is being released here. Well, considering that for every mole of this reaction, 3,013 kilojoules of energy are being released. But our reaction says that 5 moles of oxygen goes into it. Now we have 9.375 moles. So let's set this up using our dimensional analysis. Okay, so we've got 9.375 moles of oxygen times, okay, in the end, we want to know our kilojoules. Okay, we have currently moles of O2. From our reaction, we know that 3,013 kilojoules are being released for every 5 moles of oxygen in this reaction. So when you do this, you end up getting 5,649.375 kilojoules. Okay, so you could say released, you can put a negative sign, they would mean the exact same thing. Okay. So there you have it. Enthalpy talks about the heat of the reaction, indicates the heat change during reaction or physical processes, and depending on which side it is, or rather what's being absorbed or released, you can actually identify the sign of the delta H, whether it be positive or negative.